Okay, so we're going to resume where we left off, recording number 3. And now that we've plotted each of the constraints, we've identified the aggregate feasible region based on the feasible region direction arrows we've developed for each constraint. Now we're going to identify the values of the extreme points that we have. We've identified extreme points 1, 2, 3, and 4. We want to create a table for each of those, where for each of those points we identify the value of S, we identify the value of D, and then we'll use those values to calculate the objective function value, which is based on this being our objective function. So let's look at the two easiest points, extreme points, numbers 1 and 4. Number 1 is given by constraint expression, in this case A. Okay, so, pardon me, D, forgive me, constraint expression D, and so we want to identify the value of D at this point, where the value at that point for S is 0. That's clear. And what is the value of D? Well, when we solved for constraint D, if S is 0, D is 540. We take that value for 0 and 540 and plug it in here for S and D at extreme point number 1. Let's look at extreme point number 4, where it crosses the x-axis. That is associated with constraint C, so labeled. And we know that down here, the value of D is equal to 0. We've solved for constraint D, and where D is 0, right, we know that, forgive me, that is not constraint, that's constraint C, wrong one. We know where D is 0, S is equal to 708. So at that point, constraint 4, S is equal to 0, D is equal to 0, S is equal to 708, because we developed that here when we plotted constraint C. So we place those two values here in the table for extreme point number 4. Now, extreme points numbers 2 and 3 are a little trickier. Extreme point number 2 here is the intersection of constraints A and D. We have choices, but I'm going to choose to use a value to solve for A first and plug the value of one of the variables from A into expression D for constraint D right here. So let's use expression A. 0.7s plus D is equal to 630. I'll solve for D. I bring the 0.7s over to the other side. I get an expression for D that is equal to 630 minus 0.7s. Let's use this expression for D in equation D. So we get 0.7s plus 0.25 times that value we just developed right here, 630 minus 0.7s, equals 135. We use the equality expression. When we finish that out, solving for the value of S, we get this expression, negative 0.075S is equal to negative 22.5. Finish out that algebra, we get a value of S equals 300. We take that S value and plug that back up into the expression for D. When we solve for that, where we let the value of S equal 300 as we developed, we get a value of D is equal to 420. In that case, once we solve for point 2, we know that S is equal to 300, D is equal to 420. Let's solve for point number 3, the intersection of lines A and C. Again, I will solve for A, just like we did above. D is equal to 630 minus 0.7s. We put that expression into C, into expression C. When we do it, we get this expression. Then we solve for the variable S. We get an S here, 539.95. We'll round that to 540. Plug that back up into the expression for D. D equals this expression. D in this case comes out to be 252. So extreme point number 3 is where S equals 540, D equals 252. Once we know the values of our extreme points, one of these will be our optimal solution. The optimal, we plug those values for the extreme points into the objective function, max 10s plus 9d, and we get a value. When we plug 540 up into here, we get 0 plus 9 times 5, 9 times 540, 4590. Repeat for each of those other extreme point values. What do we get in terms of the largest value? Because this is a max expression, not a min. It's a max expression. The optimal solution is point number 3, where S is 540, D is 252, and the objective function value is 7668. I pray you followed along with that. We're going to do another example here. We're going to go to problem 212 on page 69 from the text, and here's what that's going to look like. So for problem 212, we are given the objective function. It's down here, max 3a plus 3b. We're given two constraints, subject to, and these are our two constraint expressions. I've labeled them a and b. So step 2, graph the constraints. For constraint A, if A equals 0, B equals 3, right? A is 0, B is 12 divided by 4, B is 3, using the equality expression. Similarly, for B equals 0, A is 6. And we do for constraint B. If A is 0, B is 6, B is 0, A is 4. Now, for each of these, we plot. So for constraint A is 0, B is 3. We go here, B is 3. And if B is 0, A is 6. This is constraint A. I've labeled it A. Which way does the feasible region go? Is it in this direction or in that direction? Toward or away from the axis? Pick a point down here, 1, 1. If you substitute 1 for A and B, you get 2 plus 4. That would be 6. Is that less than or equal to 12? Check. Yes, it is. Therefore, you know that your feasible region for constraint A is in this direction, toward the origin. Put a little arrow like that, like I do. Plot constraint B. We plot these 2 points as given over here in our calculations. I label this constraint B. Similarly, we'll identify the feasible region for constraint B. Pick that same point, 1, 1. That means that 6 times 1 plus 4 times 1, that would be 10. Is it less than or equal to 24? Check. Yes, it is. So we draw an arrow from here. But what is our aggregate feasible region? Well, A has to be in this direction. B has to be in this direction. Let me come back. So the aggregate feasible region is here, only here. It can't be in this triangle, can't be in this triangle because it doesn't satisfy B's constraint if you're over here. This triangle does not satisfy A's constraint. Therefore, for aggregate purposes, we have this, and we will have 4 extreme points. Really only 3 for practical purposes. Again, we can almost always ignore the origin unless we have a min problem. So now let's look at the value of each of these at the extreme point. We labeled each extreme point. I've labeled them so they're easy to follow. 1, 2, 3, and 4. The value of point 1 is very easy. A is equal to 0. B is equal to 3. The value of extreme point 3 is easy. A is equal to 4. A and 4. B is equal to 0. Now for extreme point number 2, okay, it's the intersection of A and B. We'll solve for A. In this case, we take the constraint A expression, 2A plus 4B equals 12. So we solve for A. We get A equals 6 minus 2B. We plug that value into the B expression. So we take 6. And we've solved for A equal to that right here. And we plug that value into the B expression. We get this. We flush this out. We solve for B. We get B is equal to 1.5. Plug that back up into this expression. Solve for A equals 3. So extreme point number 2, A is 3, B is 1.5. Do not guess. Some of you might not want to plot this out when you're doing the test. You'll simply look at the graph and hope your graph is accurate, and you'll guess. Do not guess. Go through these simultaneous equations and solve. In this case, then, we calculate the objective function value. This is our objective function for each of these extreme points. We calculate, in this case, 9, 13 and a half, 12. This is a max problem. The optimal solution, therefore, is the largest number. It's the point number 2 out here in free space where the optimal solution for that particular problem lies. All right, let's go through one more example of the graphical solution. Let's go through problem number 13. Again, from the text where we are given the objective function and the constraints, and we will solve the same way. So we're given the objective function, max 1a plus 2b. These are our constraints. There are 3 of them. Let's plot each. Let's graph the constraints. For constraint A, when a equals 0, okay, what is b equal? There is nothing. There is no b. So in this case, we use the equality expression, a equals 5. When we plot that, a equals 5 is this vertical line right here. We'll label that A. So what is the feasible region associated with that? Is it in the left direction or in the right direction? So again, let's pick a point to a test. Down here, 1, 1. It's always very easy, a convenient point. If we plug that in, where A equals 1, B equals 1, plug that into the expression here. There is no B, so we only want to concern ourselves with A. 1 times 1, is that less than or equal to 5? Check. Yes, it is. Therefore, our feasible region is in this direction. Let's plot constraint B. Similarly, just like that, B equals 4, the equality expression. That is expressed in this horizontal line right here. Let's identify the feasible region associated with constraint B. Do the test. Pick the point 1, 1 down here. 1 times 1 is less than or equal to 4. Check. That means constraint B's feasible region is in this direction and down toward the axis. All right, let's plot constraint C. 2a plus 2b equals 12. Pretty easy. A equals 0, b is 6. B equals 0, a is 6. Plot those 2 points here, 6 and 6. Connect them, and that's constraint C. Let's identify the feasible region associated with that. Well, a little trickier because it's already given as an equality expression, not as a less than or equal to. If we do 1, 1, it doesn't work out. 2 plus 2 equals 12? Nah, doesn't work out. What this means when we have the equality expression is that the feasible region for constraint C lies anywhere on this line. Now, what's the feasible region then in aggregate that satisfies all of the constraints simultaneously? That is only given as the points between, or the line between points 1 and 2, because we have to satisfy the B constraint, we have to satisfy the A constraint. So it only is are those points, these points on the line, and that's our extreme points 1 and 2. So we create a table. We know we've got points 1 and 2. Again, I'll let the third one go in there, but it's not going to apply. So points 1 and 2. Point 1 is the intersection of B and C. B equals 4 is an equality expression. Plug that into C, expression C. We get A is equal to 2. Put those values in the table. Point 2 is the intersection of A and C. Similarly, we say A equals 5. We use the equality expression. Plug that into C. We get B is equal to 1. Take those 2 values and put it in the table. Solve for the objective function, but given the values of A and B, that's our objective function right there. This is a max problem, therefore the larger value applies. That is the optimal solution. All right, I'm going to stop here, and we're going to go on to the Excel solution in our 4th recording for this week.